So I'd like to introduce the moderators for the session. We have two moderators. One of them is Dr. George John. He needs no introduction. He was a professor in Medicine Unit 3 and started the critical care division maybe more than 25 years ago out of Medicine Unit 3. He was also my chief in Medicine Unit 3. He retired in about 7 years ago and was overseas. And he has kindly joined back to help us at this time when we are very short of intensivists. And true to his character, he's plunged straight into the COVID ICU to help us with care of COVID patients. We'd like to welcome Dr. George on back. Other moderator is Dr. J.V. Peter, who needs no introduction. He's the director of the institution and also an intensivist. And he's been leading the fight against COVID over the last 1 year, both as an administrator and lately on the floor in the ICU as well. So I'll hand over to Dr. George John and Dr. Peter at this point.
Friends, welcome. We'll get straight into the topic. Oxygen has become a hot topic over the last few weeks, and one never imagined the scale of the problem that the demand-supply mismatch would cause. We have all been battling this shortage, so much so we have an interesting phrase at CMC, give us this day or daily breath. We'll first have Dr. Lallu presenting to us on the overview of oxygen management from an administrative perspective.
Thank you very much, Dr. Peter and Dr. George John, for giving me this opportunity, and Dr. Thomas Ram and the entire team. I'm going to take about 20 minutes to give an overview of the oxygen supply, the planning and the management. It's slightly technical, but I'm sure you will be able to understand what I'm talking about, because most of you are now completely into oxygen in your hospitals. So this is going to be my presentation: the types of oxygen sources, supply of oxygen backup, estimating the needs, current situation in our hospitals, planning of the system, the good practices, and disaster management. Though it looks long, it's going to be exactly 20 minutes. So this is not new to us. This is the liquid medical oxygen, which is the LMO. So what is this? This is a cryogenic source. It's in the form of a liquid. And this is the most popular choice for big hospitals and hospitals with very good connectivity, because this is not generated in the hospital. It has to come from industry. It has to come from a source. So you need to have very good supply chain to get this liquid medical oxygen. There are stringent licensing requirements. You need to have 9 meters of clearance around the vessel. This is the cleanest source, greater than 99% purity. So if you have very good ICU backing, then certainly you will need to have your LMO. As I mentioned earlier, oxygen is stored in the liquid state. Now, most of you will get confused with this. In some literature, it says 842 liters comes out of 1 liter of liquid oxygen. That's the UK norms, because UK has very strict guidelines. The HTM standards are available. Most countries follow their own guidelines. But with our situation, with the kind of temperature that is in our country, it is about 888 liters of oxygen that is produced by 1 liter of liquid oxygen. Now, this is a very complex situation. You buy it in kilogram or metric tons. You pay in cubic meters of liquid. You consume it in liters per minute, gas. So from tons, it is to cubic meters of liquid. And finally, when you are billing for your patients, it is actually liters per minute of gas. So this is a broad conversion ratio that is to be remembered. 1 kg is about 0.867 liters of liquid oxygen, which is about 0.769 cubic meters of gas. And 1 cubic meter is about 1,000 liters of gaseous oxygen. So this is something you'll need to remember. Now, vessel to vessel, there are variations with the diameter, the height. So how much each vessel can store is dependent on the supplier. And there's something known as a conversion chart that is available with each LMO and the supplier, which you will need to go through. Now with this, I will move on to the next source, primarily used in most hospitals, which is the manifold. Not all hospitals can afford to have a liquid medical oxygen supply. So this is typically how your oxygen manifold looks like. There are two banks, the left bank and the right bank. Both the banks will have to be connected with full cylinders because one bank is a backup for the other bank. It will be only one bank that will be functional at one point in time. When the pressure comes down, you need to have the auto switch over to the other bank. So this is completely pressurized and this is a good system. If you don't have both the systems connected, then it's going to be a failure. So you need to have both the sides connected, the left bank and the right bank. So what is this manifold? This is the main supply for small hospitals. And this is the first level of backup for hospitals with the liquid medical oxygen when you have your own LMO. As I mentioned, both right bank and left bank need to be pressurized. And the type of cylinders that we use is the D-type cylinders. Now the nomenclature again differs from country. In UK, you have this D, E, F and J. In India, we have this A, B, C and D. So what is connected to this manifold is actually the D-type cylinders in Indian nomenclature. So these D-type cylinders hold about 6.7 cubic meters. And the purity is very good because oxygen directly by filling stations. So it is over 99% purity. This is a small ratio that you will need to remember also here. Common types of cylinders that we use in India. A-type, which is basically the 5-liter capacity of water. That's what is written there, you know, when you see that 5 liter, don't get confused. It is not 5 liters of oxygen. It is 5-liter capacity of water. And there you will have 1 cubic meter of oxygen. And this is connected to your anesthesia machines, the very small ones that are connected to your Boyle's machine. Then you have your B-type cylinders, which is used for transporting patients. This is the small cylinders that we have in our wards. That's 10-liter capacity of water that has about 1.47 cubic meter. Those are used for transporting. Then you have your C-type cylinders, which is 44-liter capacity. These are, I'm sorry, this is a D-type. And these are the bulk cylinders that we use in our manifold. Now, this is typically a question that is asked often, and recently I had this 2 days back. Somebody just sent a gauge and the type of cylinder there and asked, I'm going to transfer my patient. How long do you think the cylinder is going to last? Now, if you look at the dial, it is the gauge reads the pressure. And here this person told me it's about 150 liters of oxygen. No, the gauge there reads the pressure. The full cylinder pressure is about 138 bar. And if you read this gauge, it is about 130 bar, which shows that the cylinder is about 94% full. So 94% full, it means it will have about 6,110 liters of oxygen, gas. This is not liquid, this is gas. So if your patient is on 2 liters per minute, you can take this patient from probably Kanyakumari to Kashmir, 50 hours of oxygen supply it will have. If the patient is on 4 liters per minute, 25 hours. So how do you calculate this? It has about 6,110 liters. And then you convert 2 liters into 60 minutes into 24 hours, divide, and then you will know exactly how many hours it is going to last you. Now, typically this cylinder, this D-type cylinder, when you are connecting to a machine, to a ventilator, CPAP, BiPAP, it can work up to 6 bar, which means the pressure up to which the machine can take. So if it is not connected to a machine and if it is directly through a mask or a nasal prong using a flow meter you're connecting, it can go up to 2 bar, which means till the end. So this is how we calculate how long it works. This is the oxygen concentrator. We keep hearing about this concentrator everywhere. This is not the small concentrator, the portable one. This is the large concentrator, the industrial concentrator that we can have in your establishment, in our hospitals. This will provide constant source, but you need to have electricity supply. What is the principle? It separates oxygen from the atmosphere. It absorbs the oxygen. The adsorbent material is silicate. It's the aluminum silicate. Purity cannot go up beyond 95%. It is about 90 to 95%. What are the impurities that are present? Some argon and some amount of nitrogen. If you need to have good flow, then at least you can load the system only up to 75 to 80%. There are two technologies available. One is the pressure swing adsorption and the vacuum swing adsorption. The pressure swing adsorption is the most commonly used. BSA is a proprietary technology. It's patented. Only some companies are providing this. Now, I'm moving on to the supply part of it. Now that we have seen what are the sources. When you are designing a system, you need to really bear in mind the three components or the backup you need to have: primary supply, secondary supply, and the reserve supply. This largely depends on the size of your hospital, the complexity of operations, which is what kind of patients are you admitting, the intensive care, the higher specialty care that you're providing, the quantum of oxygen that is required for your patients, and also the distance or the proximity to the oxygen generation plant, because supply chain is a very important concept. If you are in an area which is probably a hilly region and the supply is going to take you 6 to 7 hours, then LMO is not going to be a first choice. So you will need to, these are some of the factors that you will need to consider. This is a very important table, and I think you will have to remember this table. Now, if your primary supply, there are three main things I mentioned: cylinder related manifold, liquid medical oxygen, and the oxygen concentrator. Now, if you're a small establishment and you have manifold, it's not only one manifold. You have to have backup and another backup. So the primary source here is your manifold with an auto changeover system. You cannot depend on your technologists and technicians to go and change over for you. It has to be an automatic manifold changeover system. What is the secondary supply? Near to your existing system, you need to have a manual emergency cylinder manifold, which should take care in case there is a small problem in this particular manifold, your primary manifold. So this automatic system should provide supply for at least 4 hours. That's your secondary supply. Then you also need to have a reserve supply, which should be elsewhere. Need not be as large as the primary supply, but it should be in a location which is away from the primary location. So you should have it in another building or probably in the same building in another location and a separate connection. Now, if you're having ICUs, you can ignore the first part and just have only your ICUs also connected as a reserve supply, because that is your critical load. Now, most important thing is when you have your liquid medical oxygen, there are two things that you have to remember. You can either have a single vessel or you can have two vessels. Now, when you have two vessels, you can have both the vessels in the same location, or one vessel in one area and the other vessel in another area. So there are three things that you have to remember. If it's only a single vessel, then your secondary supply certainly will have to be an automatic manifold system. You may not use it at all, but you need to have that 24 hours pressurized. Then the reserve supply, again, you will need to have another manifold or only your ICUs or HQs connected with a separate manifold. Now, if you have one vessel and the two vessels are in the same area, the first vessel should have a separate line, second vessel should have a separate line, which means the first vessel is a backup for the second one and the second vessel is a backup for the first one. Again, the reserve here is an automatic manifold. The third aspect is one vessel and another area you have another vessel. So this is a system which is safe, where you're not putting all your eggs into one basket. You have one vessel. If that fails, then you have a secondary vessel which will take over. And again, your reserve supply here will be your automatic manifold for the entire hospital. Now, the third aspect is your oxygen concentrator. If you have an oxygen concentrator that can supply to your entire hospital, your backup then becomes a single vessel. You can have it as a backup. Just keep a single vessel, or you can have an automatic manifold system with auto changeover. And a reserve, again, as I mentioned, auto manifold, second one, or just connect your ICUs and HDUs. This is very, very, very important. 3 levels of backup is critical. Now, this is something about our network. What is the kind of backup that we have? We have 3 liquid medical oxygen plants, 11 KL, and we have 2 separate lines coming from these 3 liquid medical oxygen LMO tanks, 33 KL tanks. Then they go to separate buildings. So each building, if one fails, it doesn't mean the other building is going to fail. The other one takes over. And we have about 4 liquid medical manifold in strategic locations in our hospital that can take on the load for up to 4 hours. And we also have a concentrator that can actually take over the load of LMO, or it can connect separately to 2 buildings. So and also our OT has a separate manifold system. So there is backup to backup to backup available in our system. Now, the third part, how do you calculate oxygen needs? Now, at this point in time, it's very difficult to say, okay, I should have done this earlier. But yes, we can at least certainly look at how we are going to plan for the third wave. There are 2 methods that I used. One is the historical oxygen use, which is your back data. What you have, if you have the data available, then you could use this to plan. The second aspect is if you are building a new facility, how do you calculate the facility level estimate. So what is your goal? It's the same. The data, the historical data for historical oxygen use, and for facility level, the number of general beds, critical care beds, and the kind of plans that you have in your mind. But what you need to remember is you have to plan for 100% occupancy. The mistake that often people do is you calculate 100%, then you build up your system saying, I have only 50 to 60% occupancy or 35 to 45% occupancy. That's the problem why we have situations like this happening today. So what you plan, 100% peak load, that is what you need to keep as a system or develop as a system for the oxygen needs of your hospital. This is a WHO way of calculating the peak load. So what they say is, for if you have 700 standard general beds, you may not have points for all 700 beds. You may only keep for probably 6 beds, 1 oxygen point. But while you are calculating, you will calculate for all the beds at the rate of 0.75 liters per minute. It's not that you are going to give 0.75. You may give to the patient 4 liters. But while you're calculating for 700 beds, 0.75 liters per minute is what you calculate. For critical care beds, if you have 100, then you calculate for 10 liters per minute. Now your peak load calculation for this 800 bedded hospital is 1525. So in order to cater to this 1525 liters per minute, you need more than 10,135 D-type cylinders, which is humanly not possible. It's a huge supply chain that you're banking on. Or at least 2,000 LPM PSA oxygen concentrators, or 2 numbers of 5 KL liquid medical oxygen plants. Now the decision that you need to take is dependent on this and your economics, the feasibility, how far are you from the setup, the financial implications, all that has to be worked out. Average consumption will be only 35 to 40% on a daily basis. But as I mentioned earlier, you have to plan for 100%. Now, this was a very recent study that was conducted. Where are we in India? The current situation in Indian hospital. Now, this was done after the first wave by Jubilee Mission Hospital. And what they have identified is about 12% of the hospitals, 30 hospitals that they sampled, only had oxygen concentrator. 40% were banking on liquid medical oxygen. And the main problem is 48% dependency on cylinder manifold, which is what is hugely affected by the supply chain problem in the country. Now, the reserve oxygen supply, the third level of backup, if you look at it, it's very, very minimum in our Indian hospitals. Now, the alarm systems to see how much the pressure is dropping, you need to have central and also the zonal wise. More than 12% of the hospitals did not even have an alarm system to say that the pressures are dropping. So you're actually dependent on the patient, whether he is becoming sick, and then you are deciding whether the oxygen flow is there or not. That's actually the problem. This is just to give you a glance of what it is in our country. Now, while you're planning systems, these are some of the good practices that you'll have to remember. Certainly auto changeover from supply to backup. You cannot depend on your technicians and to say, I'm looking at it every minute. Common mistake that people do is to put a single pipeline to save cost from the primary source. You need to have 2 or 3 pipelines going. So there is no difficulty when one fails. Cylinder manifold should not be placed closer to the LMO or even closer to your oxygen concentrator. It has to be away from that. Reserve supply at any different location, even if both are manifolds, you need to have the reserve supply available. Manifolds and concentrators can be kept at higher flows, not in the basement, particularly in areas where you have floods. And we all know the example of Miot Hospital and what happened during the Chennai floods. So to mitigate the floods and other disasters, it's even better to have your concentrators in the rooftop or at a higher floors. Primary supply should meet requirement for at least 4 days and reserves for at least 3 days. And please remember, your small transport cylinders, B-type cylinders, can never become reserves for you. That is another common mistake that people do. So also along with all this, you need to have disaster planning, particularly in our, the situation that we are facing. Hourly monitoring is critical. You do not know when what is going to happen. Oxygen conservation measures, the oxygen audit stewardship program, particularly involving the nurses in the stewardship program, is extremely critical. And I'm sure our friends are going to be talking about the stewardship program and oxygen conservation measures. Also to offset some loads, use portable concentrators, and to reduce reduce the surgical load. Frequent audit on pipelines and terminal ends, because often you will notice that the terminal ends are kept open. Patient not on oxygen, patient may be on oxygen, but he may have removed the mask and thrown it aside. So that will be releasing the oxygen, and that's again a fire hazard. And also another important thing that I have learned recently is to use medical air instead of oxygen for anesthesia machine. Thanks to our anesthesia team, we are saving about 400 liters per hour for an adult patient. Thanks to Dr. Raj Sagayandan. I think these are things by which we can certainly conserve. And alert levels to be fixed. You need to have your oxygen monitoring committee to say 2 days of load. That is going to be my alert. I'm going to alert everybody. And the core oxygen monitoring group has to be alerted to say, this is my escalation matrix, and this is how I'm going to escalate to the government, not 2 hours, 3 hours supply. So we need to get ready and prepared, because very, very important to evacuate patients in case there is a problem. And a clear-cut disaster management protocol, because we may not know what is going to happen next. So these are all components of a good disaster management planning as well. And to have your team, particularly the core team, monitoring this on an hourly basis. So thank you so much. And I must really thank my tutor, Mr. Rajshekhar, the engineer in our medical gas section, Mr. David Chandran and Dr. J.V. Peter for all the inputs and support. Thank you.
Thank you very much. That was a very erudite presentation. Questions will be asked at the end. Our next speaker is Dr. Kishore Pichamuthu, who was a brilliant student during his undergraduate days, continued to be brilliant postgraduate and super specialty. He is a very good teacher, and I'm sure that he will make explicitly clear whatever he says. And Kishore, we welcome you to the meeting. Please start. I won't hold you back anymore.
Thank you, sir.
He's an intensivist in our critical care division.
Okay, thank you very much. I'm just going to be sharing my screen. Okay, so thank you for asking me to speak on oxygen conservation in the ICU. And this is something that a lot of this is something that we've learned over the last couple of weeks, and particularly in discussions where Dr. George John has been a primary contributor of a lot of the information that I have learned from. So why is it important to look at oxygen conservation in the ICU? When we're looking at oxygen conservation, ICU is one of the largest consumers of oxygen. In an audit done here in CMC, I think our ICUs consume about 350 cubic meters of oxygen a day. So that's almost 0.5 KL. And and this is, remember that there are, this is for about 12 patients. So few patients consume a lot of oxygen. And so it's very critical to look at how we can reduce the oxygen consumption in the ICU. So what we will look at is one very common question that comes up when we talk about oxygen conservation in the ICU is, how much oxygen do ventilators consume? So we'll take a look at how we can calculate that. And then we'll look at what strategies we can do in terms of the ventilator and its settings, what we can do in terms of patient strategies, choices of devices, as well as some system level interventions in the ICU. So to look at how much oxygen ventilators consume, it is important to remember that the total gas outflow of a ventilator is constituted by the minute ventilation, which is the tidal volume into the respiratory rate. The bypass flow, this is a flow that is constant through the tubings that allows the ventilator to detect spontaneous efforts and also to support spontaneous efforts of breathing. And the third is leak compensation, in the sense that all systems have some small amount of leak, and most modern ventilators will increase the flow to compensate for this leak. So if we know these three components, it is very easy to calculate the total gas outflow. And of course, the fraction of oxygen into this total gas outflow is the amount of oxygen consumed. As an example, if the minute ventilation of a patient on a ventilator is 10 liters per minute, and the leak volume, this number we can usually find in the ventilator has monitors and displays it as well. So this is about 2 liters. And if this ventilator has a base flow of 6 liters per minute, then the total flow is 10 plus 2 plus 6. And if the fraction of inspired oxygen is 0.6, for example, then the total oxygen consumption per minute comes to about 10.8 liters per minute. That is about 650 liters per hour. So that means 1D to give it a 1D type bulk cylinder will last about 10 hours. Remember, you cannot run the whole cylinder down, so it will last about 10 hours. Now, this is only a rough calculation. There will be variations from this calculation. That would depend on the type of ventilator. Some transport ventilators, for example, where the gas pressure, the oxygen pressure itself drives the ventilator, will consume much more oxygen than what we calculated. Turbine-based ventilators, some of the newer models of ventilators are turbine-based. They do not use a compressed air source. And these ventilators tend to use a little bit more oxygen than what we calculate. A rough rule of thumb is to add 10 liters per minute to this calculation that we just did. The typical standard ventilators are the compressed gas ventilators, and that they would usually go by this formula. We should remember that in NIV, as opposed to invasive ventilation through an endotracheal tube or a tracheostomy, there is more leak and there is a bit more leak compensation, and that would affect this calculation in the sense that the leak compensation would be much more sometimes than even the minute ventilation. So now that we've looked at how much oxygen is consumed by the ventilator, what can we do to reduce the oxygen? What can we do in terms of ventilator settings? The first thing to remember is that invasive ventilation by itself actually saves oxygen. If in this calculation you saw, that this patient scenario, about 10 liters. Most patients would consume about 15 liters or 20 liters per minute in the maximum. Other methods of ventilation like NIV or even high flow or even certain grades of Venturi devices use much more oxygen than that. So invasive ventilation typically uses less oxygen than other types. The second thing to remember is that these patients with COVID and COVID ARDS, we are ventilating them using a strategy of lung protection. Our ventilation is tailored to reduce the injury caused by the ventilator on the lung. Now, this is interesting because these very concepts of lung protective ventilation also help to conserve oxygen. So that means let's look at what are these steps that we take to reduce ventilator-induced lung injury. We know that we are pushing air in, and therefore all the components of this pushing effort, that is the tidal volume, the flow, the pressure, driving pressure, the respiratory rate, and inadequate PEEP. All of these actually can injure the lung. And therefore, if we can tune these to reduce lung injury, we also will be able to save oxygen. Now, COVID lungs, particularly in the first 10 days or so, they are very high compliance or normal compliance lungs, and therefore they are very prone to ventilator-induced lung injury. And therefore, it's very important to make sure that we are using a lung protective ventilation. And the first concept is to use a low tidal volume. So we use only 4 to 6 ml per kg of ideal body weight. Now, this itself will reduce the minute ventilation and therefore reduce the oxygen consumption as well. If we are looking at the in a controlled pressure controlled ventilation, we make sure that the driving pressure is less than 15 centimeters of water. Now, these two go together. So irrespective of whether you're doing volume control ventilation or pressure control ventilation, you look at both the driving pressure and the tidal volume and make sure that they do not exceed these cutoffs. We also make sure that the rate is as minimum as possible, remembering again that a higher rate also injures the lung. And a higher rate also means higher minute ventilation, which means more oxygen consumption. So that means we do not target a specific carbon dioxide. Even if the carbon dioxide is high, and we should not be increasing the minute ventilation to bring it down unless the pH is affected. Unless there is a respiratory acidosis with a low pH, we shouldn't be actually increasing the minute ventilation. So it's important to allow the carbon dioxide to be elevated if the pH is all right. The last consideration is optimal PEEP. PEEP allows us to keep the lung open, which means that we are able to prevent atelectotrauma to the lung. And it also allows us to use lower fractions of inspired oxygen. So that means if we were to keep this ARDS lung alveoli open optimally, that means we would get away with using less oxygen. So there are many ways to deciding what the optimal PEEP for each patient would be, which is out of the scope of this talk. But it's important to remember not to hyperinflate or underinflate. If we are using too little PEEP, then a large portion of the lung may be actually collapsed. That leads to an increased shunt fraction, and which leads to an increased oxygen requirement. On the other hand, if we hyperinflate the lungs, that could, of course, cause damage to the lungs, but it could also cause an accumulation of carbon dioxide, which often triggers us to increase the minute ventilation and increase oxygen consumption. So it's very important. So all these measures of safe lung ventilation also save oxygen. Other things that we can do when patients are on invasive ventilation is to use the lowest base flow setting. So that at the same time, of course, if you use too low base flow setting, sometimes triggering can be a problem. So it's important to keep an eye on that, but use the lowest base flow setting possible. It is important to monitor and minimize the leaks from various places. So this means that a regular check of cuff pressures, endotracheal tube cuff pressures, to make sure there is no cuff leak, and also actually checking tubings to see if there's a leak. A small note about operating ventilators, invasive ventilation with concentrators. Remember that most ventilators need a high pressure oxygen source. And so if you're using it with a small ventilator, it is not possible to do that unless you have a ventilator which has a specific low flow inlet. Very few models have that. Particularly transport ventilators usually have a low flow inlet. The other consideration is if you have a large oxygen concentrator, you must remember that it is not going to provide 99% oxygen, pure oxygen, and therefore, because of the lower percentage of oxygen in the oxygen supply, you will start getting constant low FiO2 alarms on the ventilator. So you must, if you're going to be switching over your ventilators to a large concentrator source, you must have a ability to switch off these FiO2 alarms. What about NIV inside the ICU? I'm sure there will be some of this will be covered in the next talk. But three important things to ensure is that there's a good mask fit in all NIV patients. Remembering that if there is an increased leak, there's an increased oxygen consumption because the ventilator is going to increase the flows to compensate for that leak. We need to use appropriate sedation to avoid hyperventilation. This is, of course, good for the lung. It avoids patient self-inflicted lung injury, but it also reduces unnecessary minute ventilation and reduces oxygen consumption. And the last thing is to use the bare minimum pressure support or IPAP. What we've seen in patients with COVID ARDS is that very, very few of them actually need a lot of pressure support. These are normal compliance lungs, and patients usually generate good tidal volumes even with zero pressure support. What they need is the CPAP or the PEEP. And so if we reduce the IPAP or the pressure support, we reduce the oxygen requirement as well. What can we do in terms of patient strategies to conserve oxygen? First is to consider the role of adequate sedation and appropriate paralysis. Now, sedation for all invasively ventilated patients, unless you're weaning them. Paralysis, we've usually found that paralyzing the patient for the first 3 or 4 days after intubation has been very helpful in reducing patient a self-inflicted lung injury, which happens because the patients have a high respiratory drive and they breathe large minute ventilations. So, adequately sedating and paralyzing, of course, controls minute ventilation. In addition to reducing lung injury, this also reduces oxygen consumption. Prone or semi-prone position, this is semi-prone. Prone position is sometimes technically very challenging, especially when we have resource limitations, when we have a massive expansion of ICU beds and we have a dilution of the competent workforce, then it's very important to be able to do just semi-prone rather than full prone. And doing semi-prone or proning improves the VQ matching and therefore improves oxygenation, reducing the FiO2 requirement, thus saving on oxygen. The next strategy with respect to the patient is to move the oxygen targets. So typically for ARDS patients, the recommendation, even before COVID times, has been a PaO2 of 55 to 70 millimeter mercury of PaO2. What we are targeting now in our patients is a 90 to 94% saturation. This is keeping in mind all the recent trials on oxygen targets. And we know that higher targets do not necessarily improve outcome. And so a lower target is adequate, does not do any harm. So this is very important. The moment you do this, you can actually start bringing down the FiO2 of a number of patients. Now you must have had the experience of patients tolerating far lower oxygen saturations than this. So it is important to remember that patients can tolerate lower oxygen saturation as long as the oxygen delivery to the tissues is adequate. So oxygen delivery is not just based on the saturation. There are two other components that we must remember. That's the cardiac output and the hemoglobin. So if these two are good, then patients tend to tolerate hypoxia much better. On the other hand, if a patient is anemic, then the patient's tolerance to hypoxia is going to be much worse. And when we are targeting lower oxygen saturation, you must remember to keep an eye out to see if tissues are getting oxygenated and to look out for signs of tissue hypoxia, whether an increase in lactate, signs of cerebral hypoxia, mesenteric ischemic pain, myocardial ischemic changes, or renal dysfunction. Another small thing that is that patients who do have barotrauma, which is not uncommon in COVID ARDS patients, small pneumomediastinums and small pneumothoraces, we used to treat with just giving them 100% oxygen and monitor the size of the pneumothorax, and that in this current scenario seems a little wasteful. So sometimes if in these kind of scenarios, if it's just a subcutaneous emphysema and a pneumomediastinum, then you can avoid using the 100% oxygen. On the other hand, if it's a small pneumothorax, consider placing an ICD early and bringing down the FiO2. The next consideration is to consider stopping inappropriate therapy. Patients who you think are not likely to make it, often they are at very high FiO2, so they're at 100% oxygen and being ventilated for a week or 2 weeks, and they are not, and you know that they're not going to make it. It is important to talk to family early and to make a decision to withdraw therapy early, so that's another way to save oxygen. Now you must remember that all these interventions, all these patient interventions apply to non-COVID patients as well, because non-COVID patients in the hospital are also consuming oxygen. What about device considerations? I'm sure Karthik will talk about it because these are used much more in the wards. But an important thing is to avoid or minimize the use of high flow nasal cannula. Now, this is of course a very provides oxygen which is humidified and reduces work of breathing. But this is one device that uses the highest amount of oxygen flows. So unless you're using very low FiO2s, at very low flows, 30 liters per minute or less and 40% FiO2 or less, the flows that the HFNC device uses is going to be very high, usually 30 to 60 liters per minute. And therefore, in this current scenario, it may be a good idea to avoid it altogether. The next consideration is to not use 40 and 60% Venturi devices, because these use 12 and 15 liters of oxygen to run. And the same FiO2s can be delivered by using non-rebreather reservoir bags, which have basically valves to prevent rebreathing. And they don't waste oxygen during expiration, because during expiration, the oxygen that's coming in from the inlet fills the reservoir bag, which is then breathed in by the patient during the next inspiration. And so at 6 and 8 liters per minute, you can actually get 60 and 80% FiO2. So, it saves oxygen when you switch from high level Venturi to NRM masks. Another thing is if a patient is on a high flow nasal cannula or a nasal cannula, using a Hudson mask or just a surgical mask on top of that has been shown to increase FiO2, therefore reducing the oxygen flow requirement. Nebulizations. Now, most nebulizations in the ICU are delivered through the ventilator, but for some ventilators, we need to use a separate nebulization. It's important to not use oxygen to drive that nebulization, but to use air or to use an ultrasonic nebulizer. Or an even better option would be to switch over to metered dose inhalers rather than nebulizers. Lastly, looking at system level interventions. Important, of course, is like was mentioned earlier, to look for leaks and to minimize them. This means that inside the ICU, one possible source of leaks are the points, the oxygen points, and preventive maintenance to ensure that there is no leak there would definitely help. Oxygen rounds, a very important thing that can be done by therapists in the ICU or nurses who are looking after the patients, is to look for leaks. Now, we have therapists who go around looking at the ventilators and their settings every hour. So they also can look for leaks to see if there's any leak at the cuff, in the tubing. Flow meters, sometimes flow meters are left open on the wall, or sometimes when a flow meter is being used, they are turned up so high that we want to use 15 liters per minute, but sometimes it's turned up so high that the flow is actually much higher than 15. But because the flow meter can only show a maximum of 15, the indicator stays at 15, and it might be much higher flows that are going through. So it's important to look at these things. And because we now have moved the oxygenation targets, if anyone has a saturation target or saturation of more than 94, the FiO2 should be lowered. One thing that can help to do this is to set appropriate SpO2 alarm. That means actually set a high SpO2 alarm at 94 so that it alarms if it goes any higher. One situation where 100% oxygen is used in ventilated patients is for suctioning. And it's important to make sure that this is brought down back to the baseline FiO2 after the procedure. Sometimes this is forgotten, and if the patient can stay on 100% FiO2 for much longer, wasting oxygen. Other things that already been mentioned, it's important to distribute critical care load. So if you have a lot of sick patients on one system, while these are patients who are consuming a lot of oxygen, it's important maybe to consider if they can be moved to another system, another hospital, so that the oxygen consumption load can be balanced. We here in CMC have been very fortunate in that we had a new hospital come up, so we were able to distribute the ICU load. We were able to shift 3 ICUs to the new hospital so that we could balance the oxygen load. And lastly, as was mentioned, to have a disaster plan. What happens if the oxygen runs out? Have a clear plan of how you're going to switch to an alternate source and evacuate patients. So these lessons that we have learned, this focus that we've been putting so much on oxygen and conserving oxygen, even after COVID, I'm sure these are very useful things to do in the ICU. Oxygen is toxic to the patient, injures the lung, and is very expensive. So conserving oxygen, even when there is no oxygen crisis, is definitely helpful. And I'm sure that this crisis will surely drive research on how we can continue to use less oxygen while getting good clinical outcomes. Thank you.
Thank you, Kishore, for your clear presentation. We'll move on to the next talk by Dr. Karthik. Karthik is working as an associate professor of medicine, and he'll be speaking on oxygen conservation in non-critical care settings.
Good evening, everyone. I'm Karthik, associate professor from Department of Medicine. Thank you, sir. Thank you, CC, for giving me this opportunity. And I would like to thank Dr. JVP, Dr. Georgian, Dr. Kishore, and Dr. Bani who suggested some of the concepts here. So let's look at oxygen conservation non-critical care setting. That is mainly in the wards. We have 2 sets of wards. That is the level 1 wards and the level 2 wards. Level 2 wards, we manage sicker patients with NIV support. So before going into the oxygen conservation, let's look into what are the different delivery devices which are available. When you look at it, there are low flow devices, high flow devices. Low flow device are nasal prongs and face masks. High flow are the Venturi and the NRM. And you have a variable performance device and the fixed performance devices. That is, your face mask will be variable and the fix will be a Venturi. You have a non-rebreathing system and a rebreathing system. So one important concept in delivering oxygen is the total gas flow should equal the peak flow of the patient. If the patient target is not achieved, the patient will go into something called what is called the flow starvation. To achieve this, you need to increase the flow, that is maintain an adequate flow, or you can add on a reservoir bag so that sufficient capacity of inspiratory limb to meet the demand, flow demand. Or that becomes fixed performance high flow system, or you can have a variable performance low flow system where you allow the room air to enter the system to meet the peak flow. And here the delivered gas may not gets diluted. So this is a nasal prong where oxygen concentration can be from 1 to 4 liters, and the FiO2 targets of 24 to 36 can be maintained. Somebody with a mild COVID ARDS, we can start off with a nasal prong, then move on to face mask if the oxygen requirement is going up, where we use for moderate hypoxia, where FiO2 targets of 28 to 40 can be achieved. If patient still deteriorating on this, we need to move on to a non-rebreather mask with the reservoir bag, where the FiO2 targets of about 60 to 90 can be achieved. So this is a Venturi mask which works on the Bernoulli's principle. It's color coded. You can give a target of 24 to 60%, and the oxygen flow can vary from 2 to 15 liters. So these are what we use in the level 1. And moving on to the level 2 wards, where we also use the NIV machines, we have three different types of NIV machine: the CPAP machine, the BiPAP, and the NIV mode of ventilator. CPAP, again, we have two types: the standalone CPAP, which gives you only the PEEP, can give O2, which can go up to 15 liters per minute, with the maximum FiO2, which can be delivered by a CPAP machine, can be only 50%. And high FiO2 can be achieved with the help of a balloon CPAP, and measurable FiO2 can be attained with which can range up to 100%. In a BiPAP machine, it has both the HEPAP and the IPAP. HEPAP behaves as a PEEP, and your HEPAP minus the HIPAP, the inspiratory flow, will behave as the pressure support. And O2 flow can be adjusted up to 15 liters here, and the maximum FiO2 achieved here can be only from 45 to 50%. As in and other mode of ventilation is a NIV mode of ventilator, which gives both the PEEP and the pressure support, and we can increase the FiO2 up to 100% in NIV mode of ventilator. So these are the different oxygen delivery devices available in the level 1 and level 2 wards. Now we'll look at what are the oxygen conservation strategies which we practice in our institute. So we have revised oxygen targets, where a target has been brought down 90 to, which is a safe target of 90 to 94%, and most of the patients in COPD is 80 to 92, and post-cardiac arrest 94 to 98%. Here we start them off with the low flow oxygen like nasal prongs, and maintain these targets, and also prone the patient so that the oxygen requirement comes down. And we also look at the work of breathing here, not the respiratory rate. If the work of breathing is going up, then we have to go up the ladder to increase the oxygen or go up to NIV mode. Then the other method is oxygen rounds. So basically, the nurses and the registrars and the respiratory therapists, they look at patients, the oxygen saturation, monitor saturation periodically, and promptly decrease the oxygen, the FiO2 once the saturation is within the target limit. And the therapists also look for the leaks. By reducing the leak, the oxygen wastage also can be brought down. And whenever there is the oxygen flow meter which is on and it's not being utilized, we need to turn off the flow meter. Then decrease the use of high oxygen consuming device. So we have moved on from venturi mask, which is a high oxygen consuming device, to a non-rebreather reservoir bag device, where with a flow rate of 6 liters, we can achieve 60% FiO2 in a non-rebreather reservoir bag, as compared to venturi mask, which will require a flow rate of about 15 liters. In patient with high flow demand, the side vent of the face mask can be opened up so that the acts as a partial rebreather mask, so that the flow starvation doesn't occur. If the patient is still distressed and flow starved, we must move on to non-invasive ventilation. So this is a picture of NRM, where, as you can see, 6 liter can give a saturation up to 60%, 8 liter up to 80%. And this is how NRM mask can be converted to a partial NRM, where the site, once you remove the valve over here, it acts as a partial rebreather mask. So flow starvation doesn't occur. Okay, balloon CPAP is a device which can be used in early ARDS to get the best benefit. And we need to use the least flow required to prevent the balloon from collapsing, so that the oxygen usage can be decreased. And for patients requiring more than 40% of FiO2 in a balloon CPAP, better will be to move them to a NIV mode of ventilator, where the oxygen consumption can be less. And we also feel that HFNO can be against the use of HFNO during this crisis. So this is a picture of a balloon CPAP, where you can see an inspiratory limb and an expiratory limb, and it's attached to the oxygen port and the medical air port, and it has a high flow meter which ranges from 10 to 70 liters. And this is an oxygen blender through which you can actually give a targeted FiO2. The advantage of this machine is you can give an higher FiO2, but the disadvantage is consumes a lot of oxygen, where your flow can vary from 40 to 70 liters. So it's better to use this machine early, and then if oxygen requirement is going up, to change out a ventilator mode of NIV in a ventilator. So what happened during the first wave is we started using the Bain circuit to recruit alveoli. As we all know, oxygenation can be improved with the help of an FiO2 or with the help of a PEEP. In ARDS, we know that early PEEP, optimal PEEP might help in improving our outcomes. So we started using Bains to recruit the alveoli in these patients. So Bains can be connected if we don't have a NIV machine or a NIV machine in terms of a CPAP or a BiPAP. So this is the how the Bains works is this is the oxygen port, and there is an inner tube which carries the oxygen, and this is the inlet through which the face mask is attached. And surrounding this, there is a outer tube through which the expired air comes out, and there is a valve here, AVL valve here, and there is a reservoir here. So what happens is that the flow starvation can be decreased because there is a reservoir bag here, and there is a PEEP valve as well, which can adjust the PEEP outlet can be adjusted. So we can start off with 15 liters of oxygen in a patient who is coming with severe ARDS, and as the oxygen requirement is coming down, how to convert a Bains into oxygen conserving modalities. As you can see, there is a Y connector here. So you can connect the Y connector to the Bains circuit and connect one to the oxygen flow meter and other one to a medical air flow meter. In that way, we can actually maintain the flow and adjust the FiO2 from the oxygen port. In this way, we can actually conserve the oxygen. And other modes of the BiPAP and CPAP use the least pressure required to overcome the work of breathing. And higher the pressure, the lower the FiO2 for the same oxygen flow used. Whenever you're coming down on the HiPAP and the EPAP, you have to realize that the FiO2 would have increased, so you have to decrease the oxygen flow rate. So this is a chart which tells what is the FiO2 delivered at different pressures. When you look at the CPAP mode, a PEEP of 6, at 2 liters, the FiO2 delivered will be 30, whereas at 15 liters, the FiO2 delivered will be 97%. Whereas when you look at a PEEP of 12, at 2 liters, the FiO2 drops to 25, and at 15 liters, it drops to 58. So as you go up on the pressures, the FiO2 decreases in a CPAP. And as you can see in the BiPAP as well, in 2 liters, when you have a IPAP of 10 and a EPAP of 10 and a HiPAP 20, you can see the FiO2 delivered is 23, and in 15 liters, the FiO2 drops down to 54. So as you go up on your pressures, the FiO2 decreases and oxygen gets wasted. Okay, the other modality, as I already mentioned, is oxygenation can be increased with the help of FiO2, that is giving oxygen, or with help of giving PEEP. What we have done is we are giving early PEEP for these patients. So what we have done is we have this modified mask. This is called the PEEP mask, where there is which can be attached like a mask. It has a inspiratory valve, and this is the port through which you send oxygen. And this is an expiratory port where there is a filter, and there is a PEEP valve attached to this. So patients who are requiring 15 liters of oxygen, once you connect this PEEP mask, the oxygen requirement can be brought down to 6 to 8 liters. And because they have inspiratory mask, there is no flow starvation here, and these patients are very comfortable. We have tried this on a few patients, and they are doing well. And the modification of this PEEP mask, when you don't have an inspiratory valve, like the NIV mask, this is an additional mask where you have a Y connector, where one limb is attached to the inspiratory port with a reservoir bag, and in the expiratory limb, we have connected a PEEP valve. So what happens is oxygen is given through this, and there is a reservoir bag here. So that will take care of the flow. So there is no flow starvation here. And the expiratory limb, we have connected a PEEP valve, which helps in giving a PEEP. And these patients will require less amount of oxygen. We can deliver about 6 to 15 liters of oxygen through these machines. And this is a modified balloon CPAP. As you can see, it has it is similar to the CPAP, the balloon CPAP, which I had shown earlier. And the difference is it doesn't have a high flow meter, and it doesn't have a oxygen blender. All that is an inspiratory limb and expiratory limb. In the inspiratory limb, what we have done is we have put a Y connector and connected one part of the Y connector to the oxygen on the wall. That is 15 liters. That's a low flow oxygen. And the other we have connected to a flow meter to a medical air. In this way, we can keep the medical air as constant, say around 10 to 14 liters to maintain the flow for the patient and adjust the FiO2 from the oxygen flow meter. In this way, we are consuming less oxygen. We're giving them a PEEP because there's a PEEP valve attached at the end of the expiratory limb. So PEEP is being delivered, flow is delivered, and we are using less oxygen. And we have tried this in our patients, and a couple of them have done well, and we were able to decrease the use of oxygen as well. So this is just a flow chart in the current oxygen constraint, how to go about with escalating oxygen therapy. So a patient comes with a COVID ARDS. If they are mild hypoxic, start them on nasal prongs and encourage proning in centrospiro, and then patient oxygen requirement is going up. If they're requiring more than 5 liters, best case scenario is to go for a trial of CPAP. If you have a CPAP machine, if CPAP machine is not available, it's going to get delayed. You don't go to a Venturi mask, but go for a non-rebreathing reservoir bag, where you can go up to say 6 to 8 liters, where 6 to 8 liters will be 60 to 80%. And trial of CPAP, you give them a trial of CPAP, see if the work of breathing is good, saturation is good, then continue with the CPAP. The work of breathing is more, saturation is good, probably try some sedation. If work of breathing is more and saturation is dropping, then we need to move on to BiPAP or a NIV mode of ventilator. So this will be the modified approach that can be taken, can be used during this oxygen crisis. So in summary, so what we have done is we have revised the oxygen targets. We have started having these oxygen rounds, and we have decreased the use of high oxygen consuming devices. And we have been trying to use the BiPAP and CPAP in an appropriate way so that can decrease the use of oxygen. We have also come up with these new innovations like the PEEP mask, which has with an additional PEEP to a low flow system, which has actually helped in bringing down the oxygen use and hoping for a better outcome. Thank you.
Thank you for the informative talk. Time for questions. I have also been asked to articulate the questions which came in the chat box so that when the video is uploaded to the YouTube, those who see it can get answers to those questions also. So we'll go in the same order. The first question is regarding industrial oxygen. What's the difference from medical oxygen? Because there's a lot of talk on Professor WhatsApp group, etc., regarding industrial oxygen causing mucormycosis and all sorts of. So what is the real difference between industrial oxygen and medical oxygen? Is there any real difference, or is it just an imagined difference?
Certainly, there is a difference, sir, with regards to the purity levels. The level, the medical grade oxygen there is an authorization that is required. The purity checks are being done very stringently. Whereas for the industrial grade, which is going to be used for steel manufacturing and other aspects, that level of purity check is not done. The second thing is the tankers and the containers that are used for carrying these. Again, the purity of these, the maintenance of these machines are certainly substandard when it comes to industrial grade. So I for once believe that there is some kind of a relationship between industrial grade and the muco that's happening now.
Thank you. Second question was, why do you need the primary source and the secondary source and reserve source in 2 separate locations?
Yeah. So if the primary source fails, let's assume there is an explosion near your LMO. And if your secondary source is also close to your liquid medical oxygen, then the proximity and also the supply, everything is going to be interlinked. So it is the same principle of not putting everything in the same basket. You need to divide the risk in such a way that it is mitigated properly and you don't put them all close to one another. So that's the basic principle.
Thank you. The third question was, an oxygen concentrator, will it be adequate for a district hospital for a 24-hour, 7-day supply?
Certainly, it will be. It depends on, the load, sir. They'll have to calculate their load very carefully and put up the concentrator to 100% of that load. Then it will be sufficient. But not just an oxygen concentrator. They will have to put an oxygen manifold as a backup, the secondary, and also have a reserve supply of another manifold as a backup. Because if this fails, your concentrator fails, and if the purity comes below 90%, the solenoid valve will stop the functioning of the concentrator if the filters are not cleaned properly, and for some reason the 90% purity is not, 90 to 95 is not reached, then your oxygen concentrator could shut off as well. So you will definitely need to have an auto changeover to a manifold in such situations. So it is not an isolated solution. All these will have to function together in such a way that there's an auto changeover from one system to another system.
Thank you. There's been one comment on the chat section that one of the differences between medical oxygen and industrial oxygen is the presence of oil particles.
It is, yes.
Those oil particles are what makes the difference between industrial and medical oxygen, in addition to other impurities. So somebody on the chat box has mentioned it. Thank you.
Thank you.
Thank you very much. To Kishore now. The question was, what determines the base flow in a ventilator and what is the lowest base flow possible in a ventilator?
Okay, so the base flow is there to allow the patient to breathe in. So when spontaneously. So when the patient breathes spontaneously, initially when the patient starts breathing in, as he is triggering the machine and before the machine responds, he needs to be able to have some gas that he can inhale. So that is why we have a base flow. If that is not there, then the patient would feel suffocated. So there is an initial triggering that happens by the patient starts breathing in, and then the patient triggers, and then the machine responds. So that period of time before the machine actually starts giving the breath, the patient should be able to take a breath. So that's why in most modern ventilators, you will have a base flow. There's a flow of air in the tubing at all times from which the patient can take the breath. The secondary utility of this is that when there is a little bit of flow through the system, it helps to maintain a steady PEEP during expiration. If there is no base flow in the system, the PEEP would slowly taper down. So these are the two reasons why ventilators have base flow. So keeping that in mind, we use the lowest. So that means if you keep a very low base flow, and the patient is a very distressed patient who's on a spontaneous or a mode of ventilation in which he's triggering most of the breaths, and he's very distressed, then if you have a very low base flow, then he will feel suffocated during that initial triggering of the breath. So you need to keep it low. What would be the lowest? That would depend on each ventilator. Most ventilators, will have about 2 or 3 options only for base flow. So you can actually select between them. So in this situation, when we have an oxygen crisis, set it at the lowest. And then if you find a patient struggling to breathe or his trigger work seems to be very high, then you can consider moving the base flow one step higher.
Okay, then what is the average oxygen utilization in an NIV mode?
Okay, so that of course depends on all those things that we mentioned. That depends on the minute ventilation, the fraction of oxygen that the patient is breathing, as well as the amount of leak. So you can actually, if the machine is able to calculate all of these components, you can use that calculation that I presented earlier.
Then you had mentioned that oxygen delivery is obviously dependent on cardiac output, saturation, and hemoglobin. Now, so long as the delivery is fine, even if the oxygen saturation dips a bit, the tissues can get their need met. What would you say is the appropriate hemoglobin level in a critically ill patient?
Okay, so not considering the oxygen problem at the moment, our usual cutoff is to say about 7 grams of hemoglobin is adequate. So we don't. So we are not changing the hemoglobin cutoff for this situation. But what I'm saying is that we should keep that in mind. If the patient has a normal hemoglobin, then I know that he will tolerate a lower saturation better. So we are not changing the cutoff or saying transfuse so that you can use lower FiO2s. The transfusion trigger continues to remain 7 grams. If the patient is having 7 grams, then you know that you'd rather keep at 90 to 94. Someone has a 15 gram hemoglobin. If he's moved down to 85, he'll tolerate it if he's got a normal cardiac output.
There was some controversy about higher hemoglobin increasing viscosity and therefore reducing peripheral flow. So whether a higher hemoglobin is necessarily useful for perfusion?
No,
What
not
is your
useful. Not useful unless there is a lot of hypoxia. So if there's hypoxia and there is adequate hemoglobin, then the oxygen delivery may be maintained, even though the saturation is a little lower. That is the only thing.
Now, someone has asked whether the base flow is 2 to 4 times the minute ventilation. I don't understand that calculation, but the base flow is much lower than the minute ventilation, right?
The base flow is much lower than the minute ventilation. As an example, some of our ventilators, Hamilton ventilators, one of the option is 2 liters per minute. The minute ventilation, of course, is not going to be so low, 2 liters, 4 liters. So it is much lower. It is not related to the minute ventilation.
All right. What is the average pressure required by a standard ventilator for its oxygen?
I can speak for the Hamilton ventilators. Our inlet gas pressure range is 2 to 6 bar. That's for oxygen. I think it's 3 to 6 for medical gas. I don't know about the other ventilators. So anything within this range is okay. So if it goes below 2, then it will not function.
Okay. And do you have an audit tool for oxygen? People would like you to share it if you have one.
The CMAI has produced an audit checklist, oxygen audit checklist. And I think, I'm sure we could share it to whoever, that could be made available.
A couple of questions on humidification. What would you use in the humidifier? RO water? What are the infection control measures to prevent infection regarding the water used for humidification?
So what we've been doing in the ICU is we've not been using water in the flow meters. Flow meters, we run it, if at all we're using, we're not using any water at all. When we use humidification for ventilated patients, the first line is to use a heat moisture exchanger. If that is not adequate, not offering adequate humidification for that patient, we move to a heated humidifier chamber. And what we are using in the heated humidifier chamber is sterile water.
Okay, thank you. For Karthik, what is the high flow nasal oxygen flow per minute, oxygen consumption? Oxygen need.
So oxygen consumption can be up to 40, it can go up to 70 liters as well, from 40 to 70 liters.
Very high.
So, very high. So that's why we don't advise the use of high flow nasal oxygen.
When do you think it will be safe to put a patient who is recovering back on an oxygen concentrator at home?
Patients recovering back on an oxygen concentrator.
Yeah, send him home on a concentrator.
So anybody who's saturation, the targets have achieved, that is 90 to 94, which is holding on for more than 24 hours. Respiratory rate is less than 30. Work of breathing is not increased. PaO2 targets have been achieved, that is more than 70 in that patient. And if they have an oxygen concentrator up to say 5 liters, we can send them home on a 5-liter oxygen concentrator.
Thank you. There's a question, can saline be used instead of distilled water in humidifiers?
So using saline instead of distilled water would lead to a lot of saline residue. Either if you're talking about the flow meters, the same thing's going to happen. If you talk about heated humidifier as well, where the whole principle is evaporation, it's going to lead to saline residues, and that's going to be hard to get rid of. So that is a problem. I don't think you need saline. There's no advantage of saline over sterile water. I think this has come up in discussions regarding mucormycosis. I'm sure mucor will be very happy with saline as it is with water. So I don't think that's going to make the difference.
Thank you. And the next question is to Lallu. And how do you sterilize oxygen cylinders before refilling? I don't know whether this is within your domain, but anyway, that's a question which has come up. I don't know the answer to that.
We don't do it, sir. We can't do it also. It is sent to the refilling agent, and I don't know whether there's any need to do that at all, because it's a one-way system. It's not going to Even if it's the virus, it's not going to go inside the, the cylinder. Maybe the outside area cleaning, if that person is asking, then probably just wipe the outside. There again, not with any chlorine agent, because that's not good for the cylinder also. So I don't think anybody is doing that. Maybe it's good to explore and see.
Thank you. There is one more question to Karthik. These patients who are sent home, do you advise them to continue proning at home?
Yes. Proning has to be continued and monitor saturation every 6 hourly. And once the target saturation is achieved, that is more than 90 to 94, you can come down on the flow rate of the oxygen that has been given. And proning has to be continued, and you can advise them on incentive spirometer as well.
Lallu, to you again. Do you do any regular checks for bacterial and fungal contamination of the supply pipeline in the hospital?
No, but with regards to the medical air, there is a purity check being conducted. But otherwise, it is the supplier's responsibility to make sure that it is medical grade and supplied to us. This is with regards to the, the liquid medical oxygen and the cylinders, the D-type cylinders. But when it comes to our own oxygen concentrators, it is the atmospheric oxygen that is taken, and that is, the oxygen is absorbed from that, and that is being supplied. There I mentioned that the purity can only be 90 to 95% max. And there are HEPA filters that actually take away all the microbes and other particles. And what you get is the residue with small amount of argon and nitrogen as impurity. Now, if it falls below that, then the system automatically will tell you that there is a higher concentration of other particles. So therefore, it won't function also below 90%.
Dr. Franklin from EMC Cochin, who wants to share something on mucor and humidifier water. We can listen to him. Let's listen to what he has to say.
So what we did is we did a full analysis of all the various water samples available in the hospital, including the humidifiers, and we were not able to identify any forms of mucor. And since it's a saprophyte, it needs some organic material to grow in. The humidifier water, nor the liquid O2, absolutely, we didn't find any of these mucorales species in it. Yes, a few of diatomaceous fungi were isolated, but that is not much of clinical significance as far as their presence in the humidifier water, sir. So this general news going around that humidifier water is the main source of mucor amongst patients, I don't think there's any actual evidence against it.
Thank you. Thank you for that input. Couple of other questions. Will you use HME on NIV?
Yeah, with NIV, HME is, heated humidifier may be better if at all you want. Mostly with NIV, you may not need to humidify at all. If you're actually using, the HME may actually increase the work of breathing. And with the BiPAP, it may be very difficult to fit a HME. HME is best fitted on a intubated patient on the ventilator.
Okay, there's one question. If your saturation is 93%, how do you adjust the BiPAP NIV settings?
If your saturation is 93%, so if your target is 90 to 94, what you're doing is fine. You're achieving the target. I'm assuming that you're saying what if the
I don't think
saturation
that is
falls?
the question. Actually, the question is about oxygen generator. The purity of oxygen is only 93%. So in that setting, how do you? That's what I think it means.
Yeah, sorry. Okay.
You titrate it to the saturation.
Yeah.
You know that the purity is low.
Correct. Finally, what matters is the oxygen saturation. And whatever
That's
you're
right.
turning the
Okay.
knob, it doesn't matter as long as you get the oxygen saturation.
Thank you. I mistook the question. Any more questions or any answers you want to share? Thank you very much. It's a time where we are all learning and we all learn from each other. And it's a whole new world, even for people who have been working at ventilators for many, many years. Keep sharing your experiences. Thank you all once again.